Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in this video I would like to take a look at a 2-transistor amplifier analyzed by my colleague Jennifer Hassler. This is an NMOS common source amplifier with a PMOS diode connected load. Professor Hassler has derived the input-output relationship according to these formulas that have an exponential form. These might look a little strange for MOSFETs that are usually written in terms of a square law, but Professor Hassler likes to operate her MOSFETs in the subthreshold region, which a lot of textbooks just call off. Those textbooks will assume that no current is flowing in that subthreshold region, although in reality there is current flowing according to these exponential laws. The general idea here is that the current flowing through the two transistors is the same, because there's no place else for the current to go. So if you just equate the expressions for the current for each transistor, you can get an expression relating the input and the output voltages. These expressions assume there's no issues with channel length modulation, which is colloquially referred to as the early effect for MOSFETs, although technically speaking the early effect just applies to BJTs. These expressions also assume that both transistors are in saturation. We'll come back to that. In the simulations I'm about to do, I'm going to assume that the threshold currents are the same, so we can ignore that last term. So ideally, we should get a straight line input-output relationship where the slope is associated with kappa N, kappa associated with the lower transistor, over kappa P, kappa associated with the upper transistor, with a minus sign. And then you can also work through this and figure out what the DC offset is. So I worked up that circuit in the RASP design tools that Professor Hassler's group has created. The VDD is going to be 2.5 volts. The triangles represent usual Xcos signals. The squares represent Modelica connections that are basically implicit connections for voltages and currents. And then we have blocks that change from regular Xcos land into Modelica land. So here we have a block that turns a Xcos signal into a voltage reference to ground. It's going to be fed by a ramp block with a slope of 1, and we're going to run our simulation for 2.5 seconds, so the input will ramp from 0 to 2.5 volts. I put an ammeter here so that we can actually measure what the current is, and I output that to a workspace variable. I'm not going to bother looking at that in this particular YouTube demo. Here I want to focus on the input-output voltage relationship, which we'll look at using this XY scope block that ranges from 0 to 2.5 volts in both axes. The blocks here measure these voltages in Modelica land and turn them back into Xcos-style signals, measuring them relative to ground. Because the Xcos blocks have their inputs and outputs in a certain fixed pattern, it's a bit hard to follow, but this does match the 2-transistor amp we saw on Professor Hassler's slide. So for the PMOS, I have the bulk connected to the source. We could play around with connecting the bulk to ground another time. And I don't know why, but in my Macintosh port of this software that was originally created under Ubuntu, and in my updating from Scilab 5 to Scilab 6, the rectangle for any new blocks that I add are smaller than the original blocks in an original schematic that I load in that was made in Scilab 5 and Ubuntu. I have no idea why that is, but it seems to simulate okay. Anyway, for my first trial, I'm going to take the kappa for the PMOS transistor and set that to 1. And I'm going to take the kappa for the NMOS transistor and set that to 1/2. So we should get a slope of 1/2. Note that I'm using a 50 nanoamp threshold current and a 300 millivolt threshold voltage. These were the parameters that came with one of the demos that came with the RASP software. I forget what the exact demo was. Okay, after 4.5 minutes of blathering, let's go ahead and hit the simulation button. Okay, it's going to simulate, and let's see what we get. Look at this nice slope we have here. I'm not going to bother to measure this in a whole lot of detail, but that looks more or less like a slope of 1/2. Or I guess I should say a slope of minus a half. Okay, let's see what happens when I set both kappas to 1. Simulate that. So this is interesting. So if we input 0, we start at an output of 2.5, and then it drops. And look at this. This is a very nice slope of minus 1, but there is a point where it starts to level out. Remember that equation that Professor Hassler derived assumed that the transistors were in saturation. When we get down to this particular regime, we're getting to a point where the NMOS transistor is entering its ohmic region, even though the PMOS transistor is probably still in saturation. Okay, now let me leave the kappa for the NFET at 1, but I'm going to change the kappa for the diode-connected PMOS transistor to 0.5. So if I simulate this, this should give us a slope of 2. Aha! So we do have this much steeper slope now. So that's probably a slope of around 2. We still have that leveling off effect that actually starts a little bit sooner now because the NMOS transistor enters its ohmic mode here. And of course, at the other end, we can't expect the output to go higher than VDD, which here is 2.5 volts. Let me dig into this linear region a little bit more. I think it would be reasonable to argue that it's relatively a straight line between an input of 0.2 and 1 volt. So that would be 0.8 volts. And over that span, it looks like it's going between 0.8 volts and 2.4 volts of output, which would be a span of 1.6 volts. So yeah, that's a slope of 2, or I should say negative 2. So let's see what happens if I were to replace this PMOS with a diode-connected NMOS transistor. So I have something rigged up for that. NMOS, diode-connected NMOS, that's what I want. Okay, so now both of these are NMOS transistors. I'm going to start with the lower transistor here, having a kappa of 0.5, and the upper transistor is going to have a kappa of 1. So if we simulate that, let's see if we get something similar to what we had previously. And in fact, we do. We have a line here with a slope of something like minus a half. Now, let's try taking both of these transistors and setting both of their kappas to 1. Let's see what happens if we do that. All right, if we simulate that, we get something that looks like something we had previously. It's starting at 2.5, sloping down at something that looks like a slope of minus 1, and then leveling off because at this point, this lower transistor is going to be entering the ohmic regime instead of the saturation regime. And for our last trial, let's try setting the kappa on the upper transistor to 0.5. This should give us a slope of 2. So hitting the simulation button, we see that we get something very different than what we had before. Instead of having a nice steep slope of minus a half and railing out at the top and then slowly sloping off down here, it's starting much lower. Instead of starting up at 2.5, it's starting at 1.4 volts. And it definitely does not have a very steep slope. So there may be folks watching this that are much more knowledgeable about MOSFETs than I am. If you have a good explanation of what's going on here, please leave a comment below. I also created versions of this using PMOS transistors as the main transistor, with the diode-connected transistor being both a PMOS transistor, and I have another version where that's an NMOS transistor. But the problem is that these versions with the PMOS transistor, for some reason, Modelica does not like these and does not want to simulate them.